Alrighty. First math video ever. Gonna start it off big. Triple integrals. Uh, just came back from class. Spent all of last week, all of spring break, doing nothing but working and trying to understand how to set up triple integrals. The weird thing was I understood double integrals just fine. Relating it to triple integrals, for some reason, I could not understand until I went to class today. It's our day back from spring break. A certain problem he did, for some reason, I finally understood it. I'll try to see if I can get you all to understand it the same way I did, because I had watched a lot of other videos on it and just didn't seem to, I don't know, for some reason I couldn't get it to apply with all of the problems I was doing correctly. So, the first thing that, let me set that aside right now. The first thing that's important is to understand that triple integrals are simply a double integral multiplied, well, not multiplied, but it's a double integral, which we'll call double integrals, are that was our formula for double integrals. Okay. Now, instead of having f of x, y, we will have double integral over d of recall for here that if we had 1 it was simply in 2 space. If we had this and we had f of x and g of x, we could evaluate a and b, our intercepts. Just say that's really crappy drawing of mine. To find the area here, we could have just done integral from a to b, integral from f of x to g of x of 1 dy dx. And that would have found our area here. Now that we want to relate it to 3 space, instead of multiplying by 1, we can now from let's say c to d f of x, y, z, dz, we can now change our height of this function. So if we want to evaluate this integral from z equals 0 to z equals 1, or let's say z equals 2, we can now evaluate a to b, integral from f of x to g of x, integral, okay, I said from z equals 0 to z equals 2, I don't know. Maybe I didn't portray that well enough. Okay, so this section here, all of this is the same as this right here. Exactly the same. Integral from a to b, integral from a to b, integral from f of x to g of x, f of f to g of x, dy dx, dy dx. And here we just put a 1. This constant 1 in here to make it just 2 space. Now we're going to say that we're going to raise the height of this up from z equals 0 to z equals 2. So now we're going to make this is f of x. This is g of x. Now we're going to go from z equals 0 to z equals 2. So now we're going to raise this up by 2 all the way around. Go ahead and shade this whole top end. I'll even get a different color here. So blue is the side of this shape, and black is going to be the top, and then there's a, it's like an eyeball shape here. Sort of a, well, I don't know, it looks just like this. Lift it up. That's how we would set up to find the integral, to find the volume of that arbitrary shape. Alright, now a example I could give. Okay, I've got this plane in 3 space here. Something I like to do with all of these is go ahead and make it z equals 1 minus x plus 2y. Alright, and we want to find the volume above this shape. Let me read exactly what it says. Under this plane and above the region, this is R, my region, bounded by y plus x equals 1 and y plus x squared equals 1. I'm going to go ahead and put these in functions of x equals 1 minus x, y equals 1 minus x squared. Alright, now something that I suggest to do with all these is go ahead and take your region in R2 and graph it so you know what it looks like. Okay, because the problem, for this instance, the problem tells you that this plane is above this region. So we know that, well, I'll show you. Alright, so I've got it graphed out already here in 2 space. Has my functions of x and y. I've got y equals 1 minus x squared and y equals 1 minus x. We know y equals 1 minus x is a linear equation. 1 minus x squared turns downwards. Up here at y equals 1. Okay, so my region is going to be the intersection of these two, this region right here. We know that the plane is going to be up above this region. Okay, so if I was to turn this sideways, so you can see it from this view, my plane, my region is going to be over here, and it's going to project onto this plane. Let's say maybe it goes like that. I don't know. Maybe it goes like that or something. I don't know what that plane does. Doesn't really matter to me, actually. All I know is that z goes from here in the xy plane from z equals 0 up to this region, and it's going to do whatever weird thing that this plane does. Alright. We can go ahead and say that z is going from 0 less than or equal to z less than or equal to 1 minus x plus 2y. Okay, and something you got to remember here is that this is going to change. The top value of z is going to change depending on where you are in the x and y plane. That's going to be important to know and realize. And that's why you got to know. That's why you got to graph this out so that you know what that top plane does. You know that it's not always going to be constant. You know that z has to be a function of x and y. Since you know that z is going to be a function of x and y, you know that you should know that that's going to be the first thing you integrate. And I'm going to have something else over here. And something else over here. Okay? If we go back to this, well, no, we don't have to go back to that yet. We can go ahead and say, remember, we want to put this function in a form like this, where we have our integral of z and then we do our regular d in 2 space, or in this case I got r. So we want to have, well, that's gonna be our problem we're gonna build off of. Now we got to figure out what our region area is in 2 space. That shouldn't be too hard. We have, what's our lower bound here for y? 1 minus x. Our upper bound is 1 minus x squared. So we know 1 minus x is less than or equal to y, less than or equal to 1 minus x squared. And we can see that up here. Now, the only reason I suggest graph this is to make sure that you, unless you can just see it right away, that 1 minus x is less than 1 minus x squared, which, I mean, not that hard to figure out. X squared is always going to increase faster than x. Okay? Now, our x values are simply going to go from here from x equals 0 to x equals 1. So we know 0 less than or equal to x less than or equal to 1. This right here is an important thing to do because that's always just going to lay out your intervals for you. Also lets you know to set it up so that you know x has no function. So that's going to be, well, the last thing you integrate. Y is a function of only x. So that's going to be the second thing you integrate. And then like we had here, 0, 1 minus x plus 2y, 1, dz, dy, and dx. Now you can solve that for your volume. And another way that you can see this relate to doing a double integral is once you solve this, or once you begin solving it, you'll find that it'll always end up at least it'll always end up this way if you start out at 0 in the z-axis. This upper bound just comes down. And now you do a double integral. And now you understand what you're doing when you do a double integral with a function of x and y here. Hope that helps, guys.